When we look at massive industrial machinery, like giant steel gears grinding away inside a factory, there's this expectation of just pure brute force, sort of like metal crushing metal.
Oh, absolutely. It feels incredibly violent, and honestly, it would be. I mean, we'd just be shredding steel into scrap if it weren't for this microscopic invisible shield doing all the heavy lifting.
Right. Well, welcome to the deep dive. Today we're looking at the hidden fluid dynamics of transmission engineering. We're exploring the concepts that engineers use to stop our industrial world from, literally grinding to a halt.
Yeah, in my 20 years consulting in high-level mechanics,
Yeah.
it's always fascinating because the scale of the machinery is huge, but the margin between success and catastrophic failure comes down to fractions of a millimeter.
Exactly. So we're decoding a professional mechanical vocabulary deck today to understand how these massive systems survive. Let's start with what actually happens when two gear teeth slam into each other. It's a phenomenon called elastohydrodynamic lubrication, or EHL,
Right.
which I have to admit sounds like a completely made-up sci-fi word.
It really does, but the physical reality of it is basically magic. When gear teeth mesh under immense pressure, two things happen. First, the metal actually deforms slightly under the stress.
Oh, so that's the elastic part of the name.
Exactly. And
Wow.
second, the oil trapped between them experiences a massive spike in viscosity. Essentially turns into a solid for a split second, forming this incredibly thin protective shield.
Wait, so it's kind of like oobleck, that mixture of cornstarch and water, where you slowly dip your hand in and it's liquid, but if you punch it, it instantly hardens.
That is a surprisingly perfect analogy, yeah.
But wait, let me challenge this. If the metal is already warping and deforming under thousands of pounds of pressure, how does the oil even have time to form a film before the metal just, grinds together?
That is exactly why engineers look at something called the pressure viscosity coefficient. It's not a slow buildup. It's a near instantaneous reaction.
Okay, so the coefficient measures that speed.
It quantifies exactly how much that specific oil's viscosity spikes the literal second pressure hits it. So in manufacturing, if you're building a harmonic drive,
Oh, those are the super high precision gears used in robotics.
exactly, you would specifically seek out synthetic oils with a high pressure viscosity coefficient to ensure that shield forms instantly. You need that rapid reaction to maintain the film's integrity right at the interface.
That makes a lot of sense. You see this a lot in modern R&D. Like if you're designing planetary gear teeth, calculating the exact thickness of that EHL film isn't just theory. It literally dictates whether the gear survives the high contact stress.
It absolutely does. It's vital for longevity.
But how do you calculate the exact operating conditions needed to trigger that shield in the first place?
Well, that is where the Strybek curve comes in. It maps out how, as the gears spin faster, they physically drag more oil into the microscopic gap between them.
Okay, so the motion itself is pulling the oil in.
Right, and that dragging motion creates enough fluid pressure to literally lift the heavy metal surfaces apart.
Oh, wow. So the curve helps engineers find the exact speed where you transition from just scraping metal to actually surfing on the oil.
Spot on. We call that shifting from mixed lubrication to full hydrodynamic lubrication. And engineers verify that they've hit that sweet spot using the lambda value.
The lambda value, also called the film thickness ratio, right?
Yes. It compares the thickness of that oil film to the surface roughness of the metal itself.
Because even highly polished metal is essentially a bumpy road on a microscopic level. So if your lambda value is over 3, which is the standard engineering rule we see in the sources, does that mean you've just flooded the whole system with oil?
Not flooded, no. It just means your oil film is finally thick enough to completely submerge those microscopic peaks and valleys. A lambda greater than 3 guarantees the gear surfaces are fully separated.
Which minimizes abrasive wear. Keep the metal apart. It's the ultimate engineering rule. But what happens if the system gets pushed past its limits and those microscopic peaks actually do collide?
Well, that brings us to the danger zone. When the film fails, the resulting friction generates what is called flash temperature.
Flash temperature, that sounds bad.
It's very bad. It's an extreme, instantaneous, localized heat that spikes right at the tooth contact point during meshing.
It is terrifying to think that the only thing stopping thousands of dollars of machinery from literally melting itself together is a microscopic puddle of oil.
It really is. And if that flash temperature goes above the lubricant scuffing limit, you get adhesive wear.
Which, as the deck points out, is just a polite engineering way of saying the gears practically weld themselves together.
Right. It really highlights how delicate these massive systems truly are. Understanding these underlying fluid dynamics completely changes how you view precision transmission.
It absolutely does. Well, mastering these terms really gives you a commanding understanding of what's happening under the hood. And I want to leave you, the listener, with this to mull over.
Go for it.
If a microscopic temporary change in oil viscosity, that little split-second Oobleck effect, is the absolute only barrier preventing the catastrophic failure of massive industrial gears, what other invisible, everyday fluid dynamics are secretly holding our modern infrastructure together right under our noses?
That is a wild thing to think about.
Next time you look at a giant machine relying on brute force, remember the invisible shield doing the real work. Catch you on the next deep dive.